discussing about another important characteristic, which is the output characteristic for a transistor. In the last classes we have seen the input characteristic of a common base transistor. Now, the output characteristic of a common base transistor we will be discussing first. The output characteristic is the graphical representation of the output current with respect to the output voltage for different levels of input current. So, if we consider the common base transistor again, here let us consider an NPN transistor which is in the common base configuration. So, the basic equations we already know, that IE is equal to IB plus IC and IC is equal to alpha times IE plus ICBO, that is the reverse saturation current, and alpha is called the common base transistor current amplification factor or current gain, and it is the ratio between the collector current and the emitter current. So, now the alpha is the current amplification factor for a common base transistor, which gives the idea about how the collector current will vary with respect to emitter current. But alpha value can be maximum 1, it is always less than 1. Typical value of alpha is 0.95 to 0.99. So, basically in common base transistor we do not get the current gain. Now, output characteristic of a common base transistor, if we want to draw, we have to plot the characteristic of IC versus VCB for different levels of the input current IE. So, this plot is the output characteristic for a common base transistor. So, here VCB, the collector to base voltage, which reverse biases the collector base junction, is in the x axis, and the collector current IC for various levels of input current IE is plotted. So, for different values of IE, if we take IE starting from 0, then increased at steps of 1 milliampere say. Now, for these different levels of IE, if we now want to plot IC by changing VCB, we get almost horizontal characteristic, that is, even though we may change VCB, we go on increasing VCB, but practically the collector current does not vary, it is almost horizontal, because the collector current is not dependent on the collector to base voltage, but it is dependent on IE only, because IC is equal to alpha times IE, and here if we note this equation, actually IC equal to alpha IE plus ICBO. Now, ICBO is the leakage current or reverse saturation current, which is very negligible. So, we can ignore this ICBO, then the equation IC will be equal to IE, which is truly represented in these graphs. As we can see that for a particular IE, if we consider say 2 milliampere, then IC will be almost equal to 2, a little less than 2, because there will be a very small base current. So, in fact, this IC will be IE minus IB, but as this base current is of the micron order, so the IC and IE will be almost equal. And this horizontal graph also represents a fact that the output resistance of this common base transistor will be very high, since for a very wide range of VCB also we are not getting any change in the IC. So, IC is almost equal to I in common base transistor, but truly it is equal to alpha times IE. So, this reason when the junction between emitter and base is forward biased, but the junction between collector and base is reverse biased, this region is called active region. So, in the active region we see that the collector current is alpha times IE, which is equal to almost IE. Now, there are two other regions also which are known as cutoff region and saturation region. So, the transistor is off in the cutoff region because here both the emitter base junction as well as the collector base junction are reverse biased. So, below this line IE is equal to 0 means here below this I is equal to 0 line we will be getting input circuit, that is the junction between emitter and base reverse biased, and this region collector to base is also reverse biased. So, this region is cut off where the transistor will be off, it will be simply switched off. Another region is known as saturation region, which is to the left of this 0. If we see this region, then we observe that the collector current is reducing and reducing. Then what was the value at for a particular IE? Say for example, if we consider this characteristic I is equal to 6 milliampere, if we go on decreasing this VCB, then if we go down below 0, that is from this point to this left side it is negative. So, we are considering a transistor which is NPN. So, if this collector to base voltage instead of reverse biasing, if it this polarity is such that it is not N is not connected to P, or if we see that this collector to base junction is say forward biased. So, what will happen if we have the collector to base junction forward biased? So, in this transistor it is NPN. So, that means this N, which is the collector, it will be having a negative with respect to the base. So, that is happening here, we are having a negative voltage VCB, or it is forward biasing the collector base junction of the common base transistor. So, as the collector base junction is forward biased, as well the emitter base junction is also forward biased, that means both the emitter base junction and the collector base junction are forward biased. So, under that situation what will happen is here, as this is N, this is P, and in the forward biased condition by this VCB voltage, the holes from this base will be travelling to the collector region. So, the IC current will be opposed by this whole current. So, the IC current will be reducing. So, it will be reducing and reducing. So, in fact, if we go on increasing the VCB in the forward direction too much, then ultimately the direction of IC will be reversed. That is very evident from this figure here. In the collector base junction being reverse biasing, the IC current was flowing in this direction from right to left. But if we now reverse it, if we forward bias it, then after compensating for the whole current, it will be now in the opposite direction. So, it will be flowing in the opposite direction to what it is. So, now we can say that it will be going to be in the reverse direction if we go on increasing the VCB in the forward bias condition. So, these three reasons are actually applied for different applications, and the saturation and cutoff are basically for switching on or switching off of a transistor. Basically, a transistor is operated under normal condition always in the active region. So, these characteristic curves show that we have no change in the collector current, even though if we go on changing VCB. Of course, we should not go on increasing the VCB in the reverse bias condition to a too high a value, because then the breakdown will be occurring. So, within the safe limit of operation, we do not see any change in the collector current. So, almost collector current is constant, which is equal to IE. In this region, if we consider saturation region, as IC is reducing, so the value of IC is not actually alpha times IE here. So, here IC will be less than alpha times IE. So, this alpha and this alpha in the active region, they are not same. So, the value of alpha will be less in the saturation region. Now, another type of transistor which is very much useful in amplification is common emitter transistor configuration. So, as we discussed, common emitter means the emitter is common to both the input and output circuits. So, here the emitter is grounded and the emitter will be common to the input circuit, which is between the base and the emitter, and the output circuit, which is between collector and the emitter. If we consider an NPN transistor, then this input circuit between base and emitter, it should be, this junction should be forward biased, emitter base junction should be forward biased. So, if we consider an NPN transistor, the emitter and base is N and P respectively. So, this base which is P, it will be having a higher potential than the emitter. So, this is the biasing, VBB is biasing it in the forward direction, and the collector base junction should be reverse biased, and that is taken care of by this potential VCC, and with these polarities when we are connecting, then it is N, collector is N and base is P. So, the collector will be at a lower potential with respect to the base, and that is ensured by this biasing voltage VCC. So, in this configuration, let us now explore into the two characteristic curves. So, in order to plot a characteristic curve, we must now vary the input voltage to see the effect on the input current. That means, here we will be varying the base emitter voltage and we will be plotting the input current, which is here IB, and for different VCE we will now see what will be happening in the input characteristic. Similarly, in the output characteristic, we will be plotting this collector current IC versus the collector to emitter voltage for different level of input current. In here the input current is the base current. So, experimentally also we can determine this characteristic curves. So, now if we consider the common emitter transistor circuit NPN transistor, we are taking for an example, and here the governing equations for the current that we discussed is IC equal to beta times of IB plus beta plus 1 into IC naught. Here this beta is alpha by 1 minus alpha, and this beta is called the current amplification factor for common emitter transistor. So, this beta is an important parameter as far as common emitter transistor is concerned, because it determines the current amplification, how much the output current is amplified with respect to the input current, that is determined by this beta value. And alpha value is very less, we know it is less than 1, but for a small alpha corresponding beta will be very large. For example, if we consider say alpha is equal to 0.98 is a typical value for a transistor we are considering, and by substituting this alpha value in this expression for beta, the corresponding beta becomes 49. So, for even a small change of alpha, the corresponding change in beta is drastic. So, that means we get a very higher current amplification in common emitter than compared to common base, and this fact is very much utilized in building common emitter amplifiers. Now, the beta expression can be simplified by simply IC by IB, because in this expression if we just observe, then the leakage part that or the reverse saturation current part, which is beta plus 1 IC naught, this is not comparable with the other component, that is IB is considerably large compared to IC naught. So, this beta times of IB is quite higher in comparison with this latter term beta plus 1 IC naught. We can very well ignore this part, second part, and we can write down IC equal to beta times of IB. So, from that the DC value of beta is obtained by IC by IB. Now, the typical value of beta, which may be varying from 50 to 400, just roughly I am saying, because every transistor has in its specification sheet or data sheet its corresponding parameters are specified, and for a common emitter transistor what will be the beta value for that particular transistor will be specified in the data sheet, and different transistors may be having a change in the value of beta, but almost it will be varying between say 50 to 400. That means we get quite high value of beta, and that is why we can get very high collector current IC even though the IB is less, because IB base current we know it is in the order of microampere, but IC will be in the order of milliampere, and in this particular configuration of common emitter transistor the input current is IB, base current. So, by varying this base current we can vary the collector current enormously. So, that is the main advantage of this common emitter transistor. So, now we will be discussing about the input characteristic of a common emitter transistor. So, as the name is input characteristic, so we know that we will be getting a plot of the input current versus input voltage, and in this particular transistor which is common emitter, in the input circuit if we observe, the input current is IB and the input voltage which will be affecting IB is VBE, that is base to emitter voltage. Now, here one point to note is that this VBB is the biasing voltage, that is VBB actually is biasing the transistor emitter base junction in the forward bias condition. But basically we have to determine the voltage across this emitter base junction which is VBE, because emitter is grounded. So, the voltage at the base terminal with respect to the emitter that is the input voltage. And in this circuit, this is a very simple circuit because there is no resistances anywhere and there is no resistive drop or any drop in the circuit. So, whatever I mean here whatever voltage is there, VBB biasing voltage, that is available at this base point. Now, if we now plot the current IB versus VBE, this VBE voltage is the voltage across the emitter base junction in the input circuit. So, this is a very familiar characteristic we know from our earlier diode, PN diode, that is, it is nothing but a forward biased diode characteristic. So, when you go on increasing the voltage across this diode, there is an increase of current which sharply increases after the threshold voltage, that is 0.7 volt for silicon. So, this typical characteristic of a forward bias diode is that input characteristic that we see in the transistor input circuit, because here if we look into this circuit, this voltage across this forward biased junction, if we go on increasing these voltage across this, then there will be increase of this base current following the typical characteristic of the diode, because the emitter base junction of the transistor is nothing but it is the diode, PN diode in the forward bias region. So, here for increment of this base emitter voltage, it will be the current IB will be rising, but this order is small, it is in the microampere range. So, for up to say around 0.7 volt, the current rise is very small and then it will be rising. Of course, it is a magnified scale, that is why this scale, if we look into, it is 0.25, 0.5 etc. So, it is not even, I mean only this is 1 volt. So, this is a scale which is a magnified scale. So, so that to see the important point where it is rising, that is the current rises after the threshold voltage is overcome, then it is almost constant. It will be, this voltage will be not changing much, although the current IB will be changing or increasing very sharply. So, this characteristic is the input characteristic of common emitter transistor. Now, here in this characteristic we have shown only one single curve, which means that we are plotting the curve or we are plotting the input characteristic for a particular value of the collector to emitter voltage. But if we now change the collector to emitter voltage, we will be getting different plots, because if collector to emitter voltage is now say increased, this reverse biasing voltage suppose is increased. Now, what will happen, that earlier also in common base input characteristic we have seen that the increment of the collector to emitter voltage, which is reverse biasing, will have an effect that is known as early effect. So, early effect means the modulation in the base width, because if we increase this collector to emitter reverse biasing voltage, VCE is increased, that means collector to base junction will have more reverse biasing voltage, because if we consider this circuit, VCE is nothing but VCB plus VBE, VBE plus VCB equal to VCE. Collector to emitter voltage, if we increase, then obviously collector to base voltage will increase, because VB is almost constant at 0.7 volt. So, now if that happens, that is VCE increment will result in the increment of collector to base reverse biasing voltage, then there will be a modulation in the base width, because if we now focus on this base width, now this base width is say WB, that is the metallurgical base width. Now, this collector base junction is reverse biased. So, the space charge region which will be formed around the junction will be penetrating more into the base region, because the base is lightly doped. So, mostly the space charge region will be available or penetrating into the base region, because of this fact that the base is lightly doped in comparison with the collector. So, as the space charge region is this, say W is the space charge region width, then the width which is WB minus W, that is the effective electrical base width in the base region, where recombination can take place. The recombination gives rise to the base current. So, now if we now increase this VCB, collector to base reverse biasing voltage, as we know that the width of the space charge region will be increasing, because it is affected by the magnitude of the collector base reverse voltage. So, as it increases means the width increases, and it will be now more penetrating into the base region. That means now W will be more. So, if we increase VCB, W will be more. So, the overall effective base electrical base width which is now available for a combination is, as it is WB minus W. So, W is increasing means effective electrical base width will be decreasing. So, that means the less recombination will take place now in this base region. So, less recombination takes place means it is less base current. So, as a result of increment in the collector to base reverse biasing voltage, we have lesser base current IB. So, that is now reflected in this input characteristic. As we can see now, VCE is increasing to the right. If we go on increasing VCE, then this curve or the plot will be shifting to right, because as IB is decreased. So, now if we see for a particular VBE, greater the VCE is lesser the base current. This IB, if we see for a particular VBE, say VBE is constant at say around 0.7 it is. So, if we now project it vertically, we can see at this voltage, this was the base current at 1 volt, at 10 volt it becomes lesser, and at 20 volt it is even lesser. So, the curves of the input characteristic will be shifting to the right and right if we go on increasing the VCE, which means increasing the collector to base reverse bias voltage. So, this is the input characteristic, and this effect of shifting of the curves to the right is because of that early effect, which is the modulation of the base width. Now, if we now see the output characteristic of a transistor, common emitter transistor. So, output characteristic of a common emitter transistor is plotted between the output current and output voltage for different levels of input current. So, now if we plot this VCE, that is the output voltage, collector to emitter voltage which reverse biasing, and IC collector current for different levels of input current means different levels of the base current, because input current is now base current. So, here are the plots. Now, IB is varied from say 0 onwards. When IB is 0 means we do not have any base current, and the equation of the collector current is IC equal to beta times of IB plus beta plus 1 into IC naught. So, IB 0 means we are left with only the leakage current or the reverse saturation current, that is represented by ICEO, that is collector to emitter current when base is open, and this represents the reverse saturation or leakage current only, because you can see here if this is open, this base circuit is open means IB is 0, then still there will be a current, the collector current will not be 0, because if you look into this equation, IB is 0, still there will be beta plus 1 IC naught. And we have to note one fact here is that it is simply not IC naught, it is beta plus 1 IC naught. So, there is an important observation we should make here, that this ICEO is not merely IC naught, it is actually beta plus 1 ICBO. ICBO was the leakage current common base transistor, but then in a common emitter transistor the leakage current is much more than the common base transistor, and this is beta plus 1 times the ICBO or ICO. So, even when you make IB is equal to 0, you are not able to make IC is equal to 0 truly, because this part of the current will be there, which is known as ICEO. The name is given because CEO means collector to emitter current when the base is open. That current will flow between collector and emitter, that output circuit. If we look into the circuit again, then this current will be between collector and emitter, even this base circuit is open. So, that is why it is called ICEO. That ICEO is the current when IB is equal to 0. So, this is the current, it is not exactly 0, it has a considerable amount. Now, if we go on increasing the IB current now, the IC current we will be getting, and this IC and IB has a relation which is beta times of IB if we ignore the leakage part, because in this region is called active region when the base emitter region is forward biased and collector emitter region is reverse biased. In this region beta times of IB is valid very much, because the leakage current or the reverse saturation current beta plus 1 into ICBO or ICE naught, that is very little as compared to beta times IB part. That is why we can make this assumption without any violation of this practical conditions, IC equal to beta times IB. So, this IC is equal to beta times IB is the plot, it is almost, this is a linear plot. So, beta is the factor which relates IC and IB, and for a particular transistor if we consider, then this beta is constant. Of course, beta cannot be kept exactly constant because of some other factors, but for the moment we are considering active region. So, it is assumed that beta is constant, beta times of IB will be the IC. So, we can actually calculate what will be the IC if we know the value of beta. So, here we see that 50 microampere IB, then it is increased to 100 microampere, 150 microampere, etc. In steps of 50 microampere we are increasing. If we now observe this plot at IB is equal to 100 microampere, IC is almost equal at constant at 10 milliampere. So, what will be the beta factor? What will be the beta value? That can be calculated by simply IC by IB. So, substituting the values of beta and IB, we can find out IC. So, in this plot we know what is IB, we know what is IC, we can find what value of beta. So, it is equal to 10 by 100 microampere. So, this is 10 to the power minus 3, we will have to multiply. So, we get this equal to 0.1 into 10 to the power 3, that means it is equal to 100, beta is 100. So, for every beta IB value we can see that same beta, that is even if you look into this 150, it is around at 15 milliampere. But exactly speaking, that IC is not constant, but has a slope to the right. That is, we can see here that IC is increasing a little to the right. When we increase VCE, there is a slight increase in IC, and this slope is much larger than the slope that we observed in common base. In fact, common base transistor was not having any slope, almost 0 or horizontal line we were getting, but here there is a slope. Now, again that effect which we have just now discussed, that is early effect, is responsible for this slope, since we know that when VCE is increased, collector base reverse bias will be increased. So, there will be increment in collector base reverse bias, means there will be a modulation in the base width, which will be reducing the base current because of lesser recombination. So, lesser recombination means lesser base current, means collector current will be higher. So, that is why collector current is a little higher in the right side when we go on increasing VCE. So, that is observed in these plots. So, this region is active region, as the emitter base junction is forward biased and collector emitter junction is reverse biased. Now, the region below this IB is equal to 0 microampere is the cutoff region. So, in order to switch the transistor off, it is not simply enough to make the IB 0, because as we have seen just now, there will be a leakage current which will be flowing, which is beta plus 1 into ICBO. That is why we have to reverse bias the reverse bias the input circuit. That means we have to reverse bias the base emitter junction, and then only the transistor will be switched off. That is why this region is below this IB is equal to 0, means it is input circuit is reverse biased, as well as the output circuit is also reverse biased. That is the region called cutoff region. So, in this region, that means the transistor is switched off. Now, the other region, which is saturation region, will be obtained when you have this VCE very small. That is, if VCE is made very small, what will happen? Because we know that VCE is actually equal to VCB plus VBE. Now, VBE is almost constant 0.7 volt. So, the collector base voltage is equal to VCE minus VBE, that means it will be VCE minus 0.7. Now, if VCE is very small, say less than 0.7 volt for silicon, then what will be the collector base voltage? Collector base voltage equal to, let us for example take VCE is equal to 0.2 volt, very small, lesser than that 0.7 volt, then collector to base voltage will become 0.2 minus 0.7, that is minus 0.5. So, what will happen when we have a voltage minus 0.5? That is equivalent to forward biasing the output circuit, because now you see that is an NPN transistor we are considering, NPN. Now, we are having a voltage collector to base which is negative, means the collector to base voltage is negative, means collector to base region is forward biased. So, if this happens, the forward biasing of input as well as output circuit happens, then similar to this phenomenon that occurred in transistor common base will be here also. So, this saturation region will be having a lesser and lesser collector current because of this phenomenon where the collector base region is forward biased when this VCE is very small. So, actually in this region a transistor is operated for switching on or saturation occurs. Now, how this saturation will be utilized in switching on, that we will be later discussing in details, but for the time being these three regions, active region, cutoff region and saturation region, these three regions we should be familiar with, and we will be utilizing this transistor in the active region, that is when the base emitter junction is forward biased and collector emitter junction is reverse biased. That is the normal or operation of a operating mode of a transistor as an amplifier. And as we earlier also discussed, in the saturation region the collector current will be less than beta times IB. In this region this beta value is not the same beta as we have in the active region, because IC is lesser and so beta will be also lesser. So, this is the plot giving the characteristic in the output circuit. Now, from these two transistor configurations that we discussed till now, that is common base and common emitter, the two key equations which are representing the two transistor configurations are, one is IC equal to alpha times IE and the other is IC is equal to beta times IB. So, these two are the key equations if we ignore the leakage part, of course. Now, one important aspect that we can see and observe then infer from these two equations is that the collector current, which is the output current, is affected by the input current. In the common base transistor it is IE is the input current, and in common emitter transistor it is IB. So, it is basically a current source which is controlled by another current source. So, it is called current control current source. The source is the input current which is controlling the output current. So, that means we are having a current source, that means IC is nothing but a current source which is controlled by another current source which is the input current. So, it is called current control current source. Transistor is a current control current source. So, if we want to change the output current, that is the current source at the output circuit, we have to do it by varying the input current source. So, that is why it is called CCC as current control current source. Now, this study of this input and output characteristics now give another relevant fact that the resistance in the input characteristic, if we see, the resistance is very low, but in output characteristics the resistance of the transistor is quite high. That fact we can very well see in these characteristic curves. There is a very little slope of this collector current. So, that means the output resistance of the transistor is very high, in the order of megohms, and in common base it is even higher than common emitter, it is almost like infinity. So, that there is no change of current even you go on changing the collector to base voltage in the common base, but here of course it is a little lesser, that output resistance R naught is little lesser than common base because of this presence of this slope. So, we have the common emitter transistor configuration having this relationship. Actually, the current relationship is IC is equal to beta times of IB plus ICEO, and ICEO is nothing but it is beta plus 1 ICBO, that is the ICBO is the reverse saturation current in common base, and it can be written as 1 by 1 minus alpha into ICBO. And if for just to illustrate this fact that how drastically beta changes for even a small change in alpha, or for a very small alpha, say 0.996, a typical value, if we take, the corresponding beta value will be alpha by 1 minus alpha, and if we substitute alpha here, we get 249, and the corresponding ICE or leakage current in common emitter transistor becomes 250 times ICBO. So, that represents the fact that common emitter transistor has a much higher leakage current than common base transistor. So, now this transistor in two configurations that we studied can be utilized with a DC source and other resistances, and also later we will be observing that it can be applied to increase the level of a signal. But before giving an AC signal to a transistor, let us first discuss what will be the analysis of a transistor with DC only. Now, so far we were not exactly discussing an electrical circuit with resistances etc. and incorporating transistor. We were only utilizing the sources to bias the transistor in forward as reverse bias. But then if we use a transistor along with other resistances etc., build a circuit with a DC source, 1 or 2 DC sources, then how to find the node voltages, how to find the branch currents, that can be discussed by analyzing the transistor circuit under DC. So, let us take one example of a circuit having a transistor in common emitter configuration, and moreover it is an NPN transistor indicated by this arrowhead in the emitter, and these are the resistances RC in the collector. Emitter has also a resistance connected to it, which is RE, and base is having a resistance which is RB. These biases VBB and VCC are there for taking care of the forward biasing and reverse biasing of the junctions. Now, we can find out the currents IC, IE and IB, and for that you have to assume VB is equal to 0.7 volt. Now, in all the analysis that we will be doing, we will be using mostly constant voltage drop model, that is constant VBE model. When the transistor is on, then the drop VBE will be 0.7 volt, and that is the drop in silicon transistor, and we will be assuming silicon transistor, and this will be followed throughout, that this constant VBE model will be used for the transistor. When it is on, it will be having a drop of 0.7 volt in the base to emitter region. Now, you are asked to show that the transistor is operating in active mode. So, in this transistor we can go to find out these currents IC, IB, IE, provided the transistor is in active mode. That has to be ascertained first, whether the transistor is in active mode operation or not. Now, to solve that and to know whether it is in the active mode, we must see whether the transistor is forward biased in the base emitter junction and it is reverse biased in the collector emitter junction, or collector base junction rather, that reverse biasing between collector and base junction and forward biasing between emitter and base junction. So, let us do that, and this circuit, in this circuit we will be now solving to find out the currents. We will be using those laws which are relevant, Kirchhoff's voltage law, current law, etc. So, in this transistor circuit, now if we look into this base emitter loop, this loop, we can apply KVL, applying KVL. Now, one important factor beta that we must know for solving this circuit, and that is given as 50. In the example, it is given as beta value is 50. So, applying KVL in the base emitter loop, we can write the equation in the base emitter loop. The voltage drops, algebraic sum of the voltage drops is 0, that is the KVL. So, start from this negative to positive rising voltage. So, it will be positive plus 5 volt. So, if we write down this equation, what will it be? VBB minus the current in this base terminal is IB. So, VBB minus IB into RB minus base to emitter drop. This is the base point, this is the emitter, this is the collector. So, if the transistor is on, assuming the transistor is on, first of all we will be assuming that the transistor is in the active region, then we will be verifying that fact by finding out the collector to base voltage, whether it is reverse biasing or not. So, let us first assume that the transistor is in active mode, and we will be finding out that VCB is VCB. So, if I write this equation, VBB minus IBRB minus VBE minus VE, the voltage drop at this emitter, that can be represented also by IERE. So, that is equal to 0. This is the first equation, Kirchhoff's voltage law we get in the loop input of the input circuit. So, now what are the values you can represent? We can substitute here. VBB is known, it's 5 volt. Now, IB. Now, IB we do not know, we have to find out IB. RB we know, VBE constant voltage drop model we have to use, it is specified. Even if it is not specified, we will assume that it is 0.7 volt drop for transistor base emitter junction. So, 0.7 volt is this one. IE we do not know, but we can represent it in terms of IB using the fact that IE is equal to IC plus IB. Now, again what is IC? Beta times of IB. So, ultimately IE is nothing but beta plus 1 into IB. So, representing that IE by this beta plus 1 IB and putting down the value of RE, now we get the equation will be now VBB minus IBRB minus VBE. This drop you do not have to forget, you will be always have to remember this drop in the transistor when it is on, minus IERE equal to 0. So, here I am replacing that IE by beta plus 1 IB, RE equal to 0. So, it will be VBB minus, I can take common this RB plus beta plus 1 into RE whole thing multiplied by IB minus VBE is equal to 0. So, we can very well find out what is the value of IB by simplification, which is equal to VBB minus VBE divided by RB plus beta plus 1 into RE. This is the value of IB. So, now replacing all the values, VBB is equal to given value of VBB is 5, it is 5 volt, VBE is 0.7 divided by RB value, RB is 50k ohm and RE is 1.8k. So, 50 plus beta plus 1, beta is given as 50 plus 1 into RE value, RE is 1.8. So, now doing this calculation I get now that IB is equal to, if we do this calculation we will be getting that is equal to IB is equal to 0.03 milliampere, or it is 30 microampere. So, if IB is this, the value of IC we can immediately find out beta times of IB. Beta is 50.03, that is equal to, this calculation will give me 1.5 milliampere. So, IC we have found out, IB we have found out. So, now we can also know IE, which is equal to IB plus IC, just representing substituting the value of IB and IC, 0.03 plus 1.5, that is equal to 1.53 milliampere. Now, we know all the currents IB, IC and IE. Now, what is needed is to find out whether the transistor is in active mode of operation or not. That means we have to know the collector to base voltage. So, if you now focus in the output circuit, again apply the KVL. What will it be? VCC minus ICRC minus VCE minus IERE, that is equal to 0. So, we can find out basically what is VCE. So, let us find out VCE. So, VCE equal to, from output circuit, Kirchhoff's voltage law, applying KVL in output circuit, that will give VCE equal to VCC minus ICRC minus IERE. Everything is known, so we can just substitute. VCC is equal to 5 minus IC we have found out 1.5, and this RC equal to, RC is given as 800 K, 800 kilo ohm, and minus IERE. This unit should be in conformity. So, I am writing it IC is equal to milliampere. So, we may not write this 10 to the power 3 because this will be volt only. And now that IE part, IERE part 1.53 milliampere into 1.8. So, that gives the value of VCE equal to 1.022 volt. So, this checking this answer, we should get 1.022 volt here. So, we now have VCE is equal to 1.022 volt. If I know VCE now, then what will be this VCB? That can be found out simply using that equation, that VCE equal to, what will be VCE? VCE, if we from this point to this point, the voltage drop is VCE, that is equal to collector to base drop plus base to emitter drop. So, writing in that way, it is VCB plus VBE, that means we can find out what is VCB, that is equal to VCE minus VBE. VBE we know 0.7 volt, VCE we have found out 1.022 minus 0.7, that gives 0.322 volt. Now, this is a positive voltage. So, if collector to base voltage is positive, since VCB is positive, and knowing the fact that the transistor which is used here is an NPN transistor, if we look back into the circuit, this is an NPN transistor. So, collector to base junction is reverse biased, because the voltage which is biasing that collector to base region is 0.322 positive. So, this point N is positive with respect to P, it is reverse biased. So, that means that the transistor is in active mode, that means it is, this assumption that we initially assume that the transistor is on is correct, because input is already forward bias, VBE is positive, we have assumed initially. So, again we verify reverse biasing, the VCB is reverse biasing. So, the transistor is, therefore, the transistor is in active mode. So, in this way we can check whether we are going in the right direction starting from the beginning, assuming that the transistor is on, we have solved this problem, and finally we are again getting or verifying that the transistor is in active mode really by finding out the collector to base region as it is reverse bias. So, in this way we can analyze a transistor circuit by simple application of this relevant laws like beta times of IB is equal to IC, alpha times of I is equal to IC for common base, and we can solve for the different node voltages as well as the currents in the branches of the transistor circuit, and that will be required for knowing in what mode the transistor is operating.